So how many people know what RAM matrices are? Okay, so all the developers. I got it. So that's what we're going to learn here. Well, as soon as you've used an MX path statement, you actually are using RAM matrices. And we'll show you how this works. So you can represent a structural model as a path diagram. These path diagrams are, these are very specific. We write these in a very specific way because when we do, we can take a path diagram and turn it directly into matrices that are optimized, and vice versa. There's a one-to-one relationship between what the computer does and what you see as the diagram. And so I personally really encourage students to think, at least think about and recognize when somebody is using a RAM path diagram, because RAM path diagrams really, they're unambiguous. And so many other path diagrams, you don't quite know what they're doing. You kind of get the idea of what they're trying to say. But with RAM path diagrams, I know if I see a RAM path diagram, I can build the matrices and fit the model immediately, unambiguously. Here we have the symbols that are used. Manifest variables are things that are measured. They're measured variables. They're squares. If you see a square in a RAM path diagram, that means there are actual values someplace. That's in a data frame someplace. Latent variables, if you see a circle, the only way that you know that there's a value in that circle is because of the model. The model is the only thing that implies values. You have no data about the latent variable. A constant is a triangle. That's that ONE, the reserved word. That reserved word is this symbol. So when you see the triangle in a diagram, you know that someplace in the model specification, somebody is taking a path from one to something else. Double-headed arrows, if they're these little loops from the same variable to itself, that means that's a variance. And you can constrain the variance to one or fit the variance. You can constrain variances to be equal to each other and all of those things. But this is a variance here is always represented whenever you want a variance. If you don't put the double-headed arrow in a RAM path diagram, that means there is no variance on that variable. And so, like for instance, and this really is possible. You can make a circle, a latent variable, that's just a dummy variable. It's a connector. It's like for Legos, but it has no variance, and so the variance is not estimated. And that's a perfectly fine thing to do. But if I see a variable without this double-headed arrow, I'm going, well, why does that have no variance? Did the person mean that, or did they just forget the double-headed arrow? Regression coefficients are single-headed arrows. And covariance is just a double-headed arrow that goes from one variable to another instead of one variable to itself. If you think of a variance, covariance matrix, what is down the diagonal? The variances. In the same matrix, the covariances are in the off diagonals. And that is represented. You'll see how that's represented in the S matrix of the RAM formula. Okay. So path analysis, you can find out what the effect is between two variables. For instance, if I wanted to find out what the effect was between this from and to, I would multiply A times B times C times D times E. And that would be the total effect between those two variables. Here it's A times B times C. So this is path analysis. And it's pretty straightforward, except it starts to get weird when you go from A to up here, so it's A times B times C, right? You have to include one double-headed arrow in any effect. So we can't just do A times B and be done. You have to find some way to include a double-headed arrow, one and only one double-headed arrow. And that means if I want to find out what the contribution to the variance of this variable is, it's both the from and the to variable. It's A times B times C times B times A. And you think, well, that's a dumb set of rules. Well, it would be a dumb set of rules, except it exactly matches the matrix algebra that you need to calculate this stuff. And we're going to go over that. So suppose I have this model. It's a univariate regression model. How simple could it be, right? Just X predicts Y, but there's also some residual. Okay, so X has a variance. That variance, in this case, since it's standardized regression, I've set that to 1. Okay, so where does that appear in the regression or the correlations between all of my variables? What are the covariances between all of my variables? And in this case, the variance of X goes in the 1, 1 position in the covariance matrix, right? And it's following the tracing rules. We've included one double-headed arrow, and its value is 1. And so we can just put it right down here. I've also represented it here. X is double-headed arrow between X and X is 1. How about for the error variance? Well, that's VE. And we can put that down here in the covariance matrix of all of the variables in the model. How about the covariance between X and Y? Well, we can follow these tracing rules. B times 1 times B, that's equal to B. B times 1. You notice I'm putting underneath these arrows, I'm putting the values on that arrow, double-headed or single-headed. And that means that I can put this covariance B in the matrix. How about the covariance between the error and the outcome variable? Well, that's also VE. Why? Because it's 1 times VE. And now we get to the spot where you can't get there from here. There's no way using the tracing rules to get from X to E or from E to X. Notice back in here in our tracing rules that the to variable always has an arrow pointing into it. No matter where the two variables shows up, there's always an arrow pointing into it. So, can you get to from E to X with arrows pointing into it? The only place where arrows are pointing into to E is with VE. So I can go VE times 1, whoops, arrows pointing the wrong direction. So how about I could go 1 times B, but then all of the arrows have to point in the same direction. Notice that other little characteristic here. Once you've made the turn with the double-headed arrow, all the arrows are pointing in the same direction. So there's no way to get from E to X. Can somebody remind me what one of the assumptions of regression is? Like the error and the predictors are uncorrelated? Yeah. And this shows that in the diagram. The errors and the predictors are uncorrelated. Okay, and so we put 0 here. And now for the fun part, but how many ways can I get from Y to Y? Turns out there's 2 ways. I can go B times 1 times B, and B times 1 times B here, and that's B squared. But also, I can get to Y as using 1 times B times 1. So the total variance of Y in a standardized regression is B squared plus B. And yeah, so if you're really up on your regression, you probably remember that as a memorized formula that the total variance in a regression is of the outcome variable can be decomposed as VE plus the regression parameter squared. Okay, so we did it. This is the expectations. But it was it's nice to do it this way, in that it kind of shows you, if you see a diagram that has all of the right components, you can figure out what each of the components of variance are, just by looking at it. Which is, I'm kind of a visual person, so I like that. But it's pretty complicated. You probably don't want to do this at home in your spare time. So maybe it would be easier. And that's what RAM algebra is. Actually, the algebra came first and then the diagrams came second, because the diagrams are just a way to represent what's going on in the algebra. There's 3 RAM matrices. There's the A matrix. That is the matrix of single-headed arrows. A is for asymmetric. And then there's the S matrix. It's the matrix of all the double-headed arrows. And the symmetric matrix. And it always is symmetric. And then there's a filter matrix that helps you, that at the end helps you decide which are latent variables and which are manifest variables. So 3 matrices. We build 3 matrices, and they look like this for this model. So X goes into Y with the coefficient B. It's a single-headed arrow. X goes into Y with the coefficient B. And E, notice I do, column goes into row. E goes into Y with the value of 1. It's fixed. So that's all of our single-headed arrows. All of the single-headed arrows in the diagram, yep. Now we put them in here. Now you're doing exactly what OpenMx does when you as a scripter write mx path from x to y, arrows equals 1. That's exactly what it's doing. It's saying, okay, you want to put something in the cell, column representing x, row representing y. This turns out to be really useful if you know what that's doing. You can take a look at the output, at the structure that was built inside the model. And inside the model will be an A matrix, an S matrix, an E matrix, or I mean an F matrix. And the A and the S matrix are going to tell you, did I do what I really wanted to do here? I use this as a diagnostic when I'm trying to figure out, well, what went on in this? Did I did this complicated thing in building the model. What actually was the result? What is going to be fit? Okay, so how many double-headed arrows are there? There's 2. That means there's going to be 2 non-zero elements in the S matrix. 1, 1 element is x goes into x, and in the 3, 3 element, VE goes into VE, or E goes into E, and this is an optimized parameter. Finally, there's the F matrix. The F matrix has a number of columns, that is the total number of variables, and the number of rows, that is the number of manifest variables. And that will mean that once you multiply that result by F, pre and post, you're going to remove the latent variables, and you can now compare the regression or the expected covariance matrix with the data, the real covariance matrix. And when we do minimization, what we're doing is we're minimizing the difference between the model expected covariance matrix and the actual covariance matrix. And that's where your fit function comes in. This is how are we going to do that? The expectation function is, how am I going to create this expected covariance matrix? Okay. Well, okay, so how many of you love matrix algebra? Okay, so the developers, and that's it. Oh, well. One more. Okay, good. And so this slide, you may enjoy this slide. This I think is one of the most fun results because you can show that I minus A must be the inverse of all the effects in the model. And what that means, if all of the effects of in the model are, we'll call that a matrix E, this is all of the, everything's effect on everything else. And that ends up being I minus A inverse. And once you've got that, you can multiply E times the S matrix times E transpose and get the expected covariance matrix. And Jack McCarver is the one who should be credited for this, and he used to say, well, that's why RAM is easy. Okay.